Chapter 5 talks about orthogonality or orthogonalization process and stuff like that. I'll try to bring in some pictures when we can in 2 dimensions, maybe even in 3 dimensions. But the idea is to set up a basis. Now, why would you set up a basis? What does that mean? What does that mean? I don't know. Let's see. I don't know if R3 is a good idea, but let's go all out and go to 3 dimensions. So let's say you're in R3, and let's say this room is your 3-dimensional space that you're working with, and let's say the origin is one of the corners of the room. I don't know which one. So pick a corner in the room. Let's say that's your corner. That one. Okay, let's make the floor on the floor. And this corner on the floor is the corner of your room. So let's say this is the corner of the room and that's the origin. And let's say now that you're standing somewhere on the floor of that room, and then you're kind of looking up a little bit at some angle. It's like there's an arrow. Okay, so you're at some other point in the room, and let's say as you look up, you can kind of define a flat plane that you're looking at. So you can think about plane point of view, and then you can have you can try to view things at your level at some plane, and then you can make your view is a three-dimensional view, so you can have you can think about another arrow going out of your head. Well, in any case, if for some reason you want to find a point in space, you can say that there is a point in space with respect to the origin on the room, right? So you can say that this point in space is, or some x value, some y value, and some z value. So that's a point in space somewhere. But what might be more interesting, is that what is this point in space relative to your eyesight in space? And so in animation, when they do those 3D animation, I just heard what's that? Pixar's first movie, Toy Story. It's like their 20th anniversary or something today, or this week, or whatever. So, from an animated point of view, you're looking at an object in 3-dimensional space from a different point of view instead of just looking at the standard origin. So, what you might be interested in is to find maybe the distance between them, or better yet, maybe you want to express this point instead of the XYZ based on the XYZ coordinate system. Maybe you want to express this point as a new x, a new y, and a new z by changing your frame. So instead of a frame coming from the origin, you have a new frame where your origin now is your eyesight, your eyes, and then you're going to have a new set of basis. So the new set of basis, the thing about the new set of basis of where you are may not be orthogonal. I mean, may not be perpendicular. So these angles might not be perpendicular to each other, and this angle may not be perpendicular to each other. So you have these angles that may not be perpendicular to each other. So in terms of trying to find a new value for the basis that you have, it might be a little bit more difficult. So the game here in this chapter is to try to make up a new coordinate system. So this is your new coordinate system, your eyesight, and then make a set of basis vectors that are not only perpendicular, all perpendicular to each other, but also if they have length 1, that will make it even better. So orthogonal basis, actually, the term that we're going to be using is orthonormal basis, where the ortho stands for orthogonal, which is perpendicular, and then the normal stands for normal, which is length 1. And it turns out that dealing with perpendicular bases of length 1 are the easiest types of bases to deal with. So if we get ourselves set up with an orthonormal basis, then we have a good set of basis vectors to go with. How many people have taken Calc 3? Are you familiar with the Frenet frame? TNB? So the T is your tangent vector, the N is your normal vector, and the B is your binormal vector. So this is sometimes called the TNB frame, where if you're moving along a curve in space, you can create, you have a tangent vector that could be as long as whatever. You have an acceleration vector that's pointing in another direction. And so between those two vectors, you can make it orthonormal. You can shrink the tangent vector to a normal vector. And then you can take your acceleration vector and somehow make it perpendicular so that you're still looking at the same plane. And then you just find your binormal vector by looking at the cross product of those two vectors. And so now you've created a 3D frame with an orthonormal basis. So if you're familiar with the Frenet frame, if you've heard that, if you've seen that in your Calc 3 class, that's kind of like what we're doing here, is to create a set of vectors that are perpendicular and have length 1. Okay. 2 dimensions, we're going to be restricted to a simple orthogonal set of bases, and you'll see that there's only one choice that's similar to something that we've seen before. But in 3 and 4 dimensions is even stranger. But 3, 4, 5 dimensions, you can create these orthogonal bases if you can create, if you're given a set of vectors that are linearly independent. All right, so that's your setup for the chapter. And let's get to our first definition, which is orthogonal, which should be pretty clear and obvious. A set of vectors is called orthogonal if you take the dot product of any two vectors and it's equal to 0. And you have to take the dot product of all the possible combinations of two vectors. So that's what this little bit of statement says. Vi.vj is equal to 0 whenever I is not equal to j. So if you take the dot product of any of those vectors, and you have to take the dot product of all of them, you'll get orthogonal vectors. So let's say you're in R3, and then I give you 3 vectors in R3. Or let's just say you're in R2. How many dot products do we have to check? So in R2, these are your vectors, V1 and V2. So I need to take 2 dot products to check? No. 1. So V1 dot V2 is the only check that we need to do. Right? So in R3, what if I have V1, V2, V3? How many dot products do I have to check? 2? Are you just guessing? 3? Let's see. V1 dot V2. We need to check V2 dot V3 and then V1 dot V3. You said 3 and 2. So there's 3 checks, right? And so you could probably figure, well, I don't know if you can figure, but we can, let's do one more. This is just to get us kind of ready for how many checks that we're going to have to do. V1, V2, V3, V4. 8? So 6? Let's see. V1 dot V2, V1 dot V3, V1 dot V4. So there's 3 of them. And then we got V2 dot what? I don't know. Wait, I lost my count. V2 and V4. And then V3, V4. 4, 5, 6. Is it 6 or 7? Wow. Something like that? I don't know. Yeah, it's a combination. It's a weird combination because you can't pair up with yourself. So, you guys know, I don't know if this is correct. Maybe I should pause the recording. 2 choose n. Have you guys heard of that combination formula? 2 choose n. You guys know how to find that in your calculators? So if you have n things and you're choosing 2 at a time, how many different combinations of those 2 things that you have? Like, let's say we have a whole class here of, I don't know, 20 people, and we want to vote 2 people to be a class representative or something like that. Then how many possible combinations do we have? It'll be 2 choose whatever this is. And so 2 choose n. Yeah, it's the permutation divided by some factorial. So I'm going off on a tangent here. I don't know. I don't really need to talk about this. But now I've gotten curious. Maybe I should have done this earlier so I won't have to talk about it with you guys. This is just for me now. So your calculators have the and choose R kind of business under math. So let's see, 2, and then the permutation, I think it's under math. No, maybe I should just do math. Probability, the NCR. Oh, I need to type in the, so 2 choose 2 for the first one is equal to 1. 3 3 choose 2 is 3, and then 4 choose 2 is 6. So it's the number of choices. So you have this in your calculator if you're interested in messing around with it, and if you're taking probability or statistics, you'll need to know where those are. So this is how many checks you'll have to do, depending on the number of vectors that you have that you're checking. By the way, this comes from Pascal's triangle, right? Did you guys know that? So if you draw Pascal's triangle, you see these numbers pop up also. It's pretty cool. And don't have time for that, so let's move on. Let's take some of these problems and maybe do determine whether the sets of vectors are orthogonal. So let's do, I don't know which one. They all have 3 except for the last one that has 4, which means we'll have to do 8 checks. So let's just do the one with 3 vectors. 1 through 5, pick a number. 2. Somebody said 2 first. Let's do 2. So let's find out whether these are orthogonal. And so we really just have to check a bunch of dot products. So we know that there's 3 vectors. So there's going to be 3 checks. So we're going to have to do 3 dot products. So 4, 2, negative 2, dot that with 1, 1, 0, 2. So that's 4 plus 0 minus 4. That's equal to 0. So that's 1 check. And then now we do 4, 2, negative 2. Dot that with the second one, or the third one, minus 2, 5, 1. That's negative 8 plus 10 minus 2. That turns out to be 0 as well. And then we just do one more. 102 dotted with negative 2, 5, 1. And fortunately, the dot product is commutative, so we don't have to check the opposite. Just do one of these at a time. So this is minus 2 plus 0 plus 2, which is again equal to 0. So number 2 looks like the set of vectors is orthogonal. So that's all you really have to do is to check whether something's orthogonal is due to dot product. Okay? All right. So that was easy. All right, if you have an orthogonal set of basis vectors, then, or orthogonal set of non-zero vectors, then these vectors are linearly independent. Well, that seem obvious? So this would be a good, in terms of math, this would be a good proof by contradiction, because you can suppose that they're not linearly independent. And then you assume that they're not linearly independent, and then you'll get some sort of contradiction. Should we do it? Nah. Yeah? Let's see if I know how. All right, let's prove this. And the course outline and record for this class, it says that it's supposed to tell you how to do proofs and stuff. We've proven stuff in this class before, haven't we? Yeah. You've even had some quizzes where you have to prove stuff, so I think we've done our job. Maybe we can just skip this proof. All right, let's not. Let's actually prove it. So the assumption proof, let's say, let's be specific here. This is a proof by contradiction. So what we're going to do is we're going to assume that you have an orthogonal set of vectors, v1 through vn. It's orthogonal. Then the conclusion for the theorem says then these vectors are linearly independent. So that's where we're going to do our contradiction part. We're going to assume that your set of vectors v1 through vn is not linearly independent. Assume. You're going to assume that they're not linearly independent. And holding true to your condition, we should get a contradiction here. Okay, so if it's not linearly independent, what does that mean? That means I should be able to write one vector as a linear combination of the rest of the vectors, right? Then, or let's rephrase it this way. Then C1, V1, scalar C and vector V plus C2, V2 plus dot, dot, dot plus Cn, Vn equals 0 for C1 up to Cn, not all 0. Let me think about this. Yeah, I don't know if this is the best way to do it, but let's try it anyways. So these are not all equal to 0, right? So let's say one of them is non-zero. So say C1 wasn't equal to 0. Okay? Formally, I would say without loss of generality, because I can just switch the numbers around. So let's just say that C1 was the one number that's, there could be a bunch of numbers not equal to 0, but let's just say C1 was not equal to 0. So what I'm going to do is I'm going to take this, this is a 0 vector, right? These are vectors, right? Well, I'm not taking the dot product yet. I'm taking a scalar times a vector plus a scalar times a vector, so the result is a vector. But now I'm going to take the dot product. So assume that C1 is the non-zero number. And then let's take the dot product. Take dot product with V1 on both sides. So this is what I'll have. I have V1 dotted with this big long vector, C1 V1 plus C2 V2 plus dot 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 plus Cn Vn equals V1 dotted with a 0 vector. Okay? All right. Now, if I remember correctly, there's these properties for dot products that we kind of learned some time ago that we kind of took for granted because we never use them. Turns out that those properties are important mainly for proving things. And one of the properties says if you take in the dot product of a vector and another vector that's being added, then you can do a distribution. So there's a couple of properties. There's a distribution property, and then when you take the dot product of a vector and a scalar times a vector, it's like moving the vector aside and just taking the dot product of the vectors. So there's two steps here. I guess I'll explicitly write it out. The first step is a distribution. I'm just going to skip this one. I'll say dot, dot, dot from here. So that's the first property that I'm going to use. It's the distribution. The next property I'm going to use is the association. So I'm going to move the scalar out and then just say scalar times the dot product v dot v. Which, by the way, is equal to 0 because I have my vector dotted with the 0 vector. So this is equal to 0. So are we good so far? So now I'm going to use the fact that the set of vectors were orthogonal. So if the set of vectors were orthogonal, then V1 dotted with Vn should be 0. And V1 dotted with V2 should be 0. And everything else here should all be equal to 0. All right? Now, V1 dotted with itself is what? It's not 0. What is V1 dotted? What's the dot product of a vector with itself? Do you guys remember? People are doing these things. Do you guys remember what happens when you dot a vector with itself? What? Not quite one. What? Are they? It's the what? It's square? Absolute value squared? Or, in other words, the length. Okay. Now, we have to assume that the length, this is a non-zero vector, that the length of so V1, the length of that is not equal to 0. So C1 has to equal to 0. Right? Yeah? Yeah, so the magnitude of V1 is equal to the square root of V1 dot V1. So if I take, yeah, if I square both sides, you get that.
Okay. Is there a word for that?
No, there should be. It's like a property of the magnitude, but there's no special name for it. All right. So are we good with C1 is equal to 0? We shouldn't be, right? Because we said assume that C1 was not equal to 0. And then we got C1 is equal to 0. So that's where this becomes a contradiction. And they use this first symbol for contradiction. Contradiction. So what that means is that you assumed the opposite of your conclusion, and then you use the conditions that's on the theorem, and then you got something that was wrong. So that means your original assumption must have been false. Assume that this is not linearly independent, so that must have been false. So that must mean that they are in fact linearly independent. Okay? Did you go for one of these on the final? A contradiction problem? A proof by contradiction? I need to throw one proof on the final. I don't know what yet. What? All right. Well, we'll talk closer after Thanksgiving. We could take a vote as to what kind of proof to put on the final, and I'll take like the top 3 votes, and then I'll pick one of them. This is a good candidate, though. You think?
Yeah.
Or would anybody vote for this as a problem to put on the final? No. I probably won't put the exact same thing. I'll put something similar to it. All right. All right, so I should, this proof is done, so I should have QED'd it. QED. So when you get your contradiction, you're done. All right, so it's clear, should have been clear, that if you have an orthogonal set, that they're all linearly independent. That's what that is. Sean? Not necessarily, but it doesn't matter in the proof. So some of these other c's may not have been 0, but I'm just picking one for sure that's not going to be 0, and that's my assumption here. Because if it's linearly dependent, that means that these are not all equal to 0. So I'm randomly picking one that's not equal to 0. And it doesn't mean that the others can be not, the others have to be 0. It can mean like all the others are non-zero. It still wouldn't matter because I just randomly picked one. To make this more general, I would have to have chosen C sub I and not necessarily that first C. Just to be general, I assume that C sub I is not equal to 0, and I'd walk through the same way the proof. I'd multiply it by V sub I, and then V sub I dot V sub I will be non-zero. And so that's where I'll find my contradiction. Okay. So another definition, orthogonal basis. An orthogonal basis for subspace W of Rn is a basis that is an orthogonal set. that seems kind of weird, but that's a definition, and that's how they say definitions. And so let's find an example. Let's say we're in R3. And let's say I have 2 vectors in R3. So subspace spanned by 2 vectors in R3. So give me 2 vectors in R3. And another one. Oh, I wanted to do this example after I give you the next theorem. Oh well, we're here. So is this an orthogonal set? They're linearly independent. So linearly independent, but not orthogonal. What does this subspace look like? So this is, I gave you the dimensionality here. We are in R3, and we're looking at two linearly independent vectors that this thing spans. So what does this span? What? So this should be a plane in R3. Okay. So this is a basis for a plane in R3. They are linearly independent, so that if they were not linearly independent, then they would just span a line, and that could be interesting, but it's not interesting because we're talking about we want 2 linearly independent vectors. So this thing spans a plane. Some 2-dimensional object in R3. Okay, so I'm going to try to use a computer to do this, but let me see if I can just do this using a picture. So 103 would probably be something like this. And -2, 1, -2, -2, 1, 5 would be over here. And then we said that this thing spans a plane, so let me draw a plane here and see how this would look like. I don't know. So that plane goes through the origin, and these two vectors are on the plane. Okay? Now, those two vectors form a basis where it gets to span the whole plane. That means if I pick any point on the plane, I can get to that point by having a linear combination of these two vectors. Okay, do you understand that part? That part is like some fundamental understanding that we should have known that I'm not sure if you understand or not. But that's what linearly a linear combination means. You take these vectors and then you multiply it by a scalar and then add it with the other vector multiplied by a scalar to get to some other point on that plane. So that's the whole idea of spanning something. At any point on that plane, I can get to that with these two. That's what it means to be a basis. Now, clearly, they're not orthogonal because you did the dot products in your head and you didn't get 0. But can I get two orthogonal vectors that would span the same plane is the question. So, well, yeah, if I just take maybe I'll keep this first vector over here, and then instead of using this vector, maybe I can find just another vector that's also on the plane that's orthogonal to that. It's perpendicular to that first one. So that's the key, is to try to find a vector perpendicular to that one. How can we do that? Cross product? We don't do cross products in this class. Sorry. Cross product won't work either. But we don't do cross products in this class. What? Invert? How do you invert? Okay, let's redo this. Let me redraw the two vectors again. And let me draw it like this. Does it look? Do you know where I'm headed with this? Projection, right? Good. So we could do a projection. Right? Do you remember the projection formula? We can do the cosine, but we can just stick with the vector dot products. So let's start calling this V1 and V2. So the projection, I'm going to say the projection of V2 onto V1 is what? V2. What? V1 squared? Times V1. Okay? So this is going to be the projection vector is going to be this vector. Right? That's what the projection means. So you project V2 onto V1, then you're going to get this vector over here. It's going in the same direction as V1, except it got scaled by something. it got scaled so that you have that length. Does that help us find a perpendicular vector? How? So this here would be a vector that's perpendicular to V1, right? So we just came up with this new vector, this red vector over here, that's a projection of V2 onto V1. That's that vector. And then we have V2. So what is this new perpendicular vector that we're interested in? Not the absolute value. I want the whole vector, not just the length. So I want the whole vector. If I have two vectors, and I want to find a vector connecting the two heads of those two vectors, subtract what minus what? Not the square root. Not V1. So it's head minus tail. So the head is V2 minus, not V1, because if it was V1, then it would be this vector. And I don't want that. So it's minus the projection of the whole thing. So V1 dotted with V2 divided by the magnitude of V1 squared times V1. So, yeah. Not directly. No, not directly. If I dig deeper, I might be able to find a connection, but I don't think so. So if I take now the vector 1, 0, 3, oh, we should probably do this, huh? Let's do this. So V2 is negative 2, 1, 5. Minus, let's do this projection. What's V1 dotted with V2? $13? 13 divided by the magnitude of V1. This is V1. So 9, 10, square root of 10, squared 10. 10 multiplied with V1, 1, 0, 3. So this is 13 tenth, 0, and 13 times 3, 39. So I need to subtract 2 minus 13 tenths, so 20, it's minus in the minus, so negative 23. This is 13, right? 33. So negative 33 tenths. 1 minus 0 is 1, and 5 minus this, 11 tenths. So now I have a new set of basis vectors, and these two basis vectors is going to span the same plane, except now I have the added bonus that these two are orthogonal. Does that make sense? So now I have two perpendicular vectors that span the same plane, and we got it by doing the projection. What was the word in the beginning of the class? It's not orthogonal, it was orthonormal, right? So how would I make this orthonormal? Make it into a unit vector. So after I do this, just shrink this down to unit vectors, and then it'll be orthonormal. Okay, we won't do that yet, but that's the idea. Okay, so what we just did is an example of the next theorem that they said, how you can construct an orthogonal set of basis vectors. So if you have a random number of vectors, oh, you already have an orthogonal set of vector. So if V1 through Vk are orthogonal basis for a subspace in Rn, and W is any vector. Oh man, this is different from what we just did. Anyways, I thought this was the same thing. All right, this is a new thing. If you have an orthogonal set of basis vectors, then there's a unique set of scalars C1 through Ck such that W is equal to the linear combination of those vectors. All right, let's do some examples of this. Seven, 8, 9. Which one should we do? 8. So a good thing about this is that they already assume that these are orthogonal. We can check that they're orthogonal. So these two are your basis vectors. How's that fancy B look like? It goes. Got a little excited there. It's all big. 3, 1, and negative 2, 6. And these are orthogonal. You guys checked in your head? So they're orthogonal set of vectors. And so now we want to find W is equal to 1, 2. And we want to find scalars. Want W, which is equal to 1, 2, to equal to C1 times the first vector plus C2 times the second vector, and we essentially want to find C1 and C2. Okay, so how we're going to do this is a system of linear equations. I don't know if you guys can do this in your heads. It's not, is it obvious or no? Nah. So C1, 3 times C1 minus 2 times C2 is equal to 1. C1 plus 6 C2 is equal to 2. And then we have two equations and two unknowns, a system. Could have just went straight to a matrix with this, right? How should we do this? Do you guys get the answer yet? I'm just kind of stalling until somebody gets the answer. Yeah.
Just from looking at this, is C1 equal to C2?
I don't know. But I actually need a number. Whatever they are. They could be, I'm not sure. Did somebody figure it out yet? Really? Which one's which? Wow. Could have done that by guessing. Are you sure? This would be 3/2. Yeah. All right, good. Good job. Thanks, Jose. So W can be equal to this. And so what these coefficients represent is the components of a new way to write the point. Okay? What this means is that you can write W, which is equal to 1, 2, as equal to 1/2, comma 1/4 with that particular basis. So what happens is that when you change the basis, you can write new components for this with a different basis. And then you can write it as if it was exactly a point or a vector. Right? So think about this for a minute. I'm going to switch screens. I'm going to go back to our first page. When you were standing in the room over here, right? And you're looking at this point XYZ. So this point XYZ is relative to the origin, and that's the point that's called XYZ. Now, if you establish a new set of bases from your point of view, let's call this basis B. And then from here, from where you are with this particular basis, you identify that point over here as a linear combination of the 3 vectors that you have. Then you're going to have new components for that. So I'll call it X prime, Y prime, Z prime is going to be the new components, and then this is exactly this XYZ, except you're using your own basis vectors. So from your point of view, you're seeing it from your distance and from your XYZ axis in your head, it's coming out of your head, you're able to get to that point by multiplying scalars to those 3 vectors, and then getting to that point from your head instead of from the origin. So that's exactly what's happening here. And you're allowed to rename it with these new components as long as you're saying this comes from a different basis. The basis for this, by the way, these values come from the standard basis vectors. And in the book they call it E1 and E2. We're in 2 dimensions, where E1 is 1, 0 and E2 is 0, 1. So this is exactly 1 times 1, 0 plus 2 times 0, 1, where each of these are your E1 and E2 vectors. So those are the standard basis vectors, but if you change basis, you can still rename your vector with the new components with a different basis. Okay? So changing basis is important for certain applications of things, and so that's what we're going to do. We're changing basis. Not only that, but we're going to make our change of basis orthogonal. Orthogonal and normal, so orthonormal. So that's what we're going to move towards. Okay? All right. So there's homework that's been kind of shifted or postponed or something. So take a look at WebAssign to see when the homework assignments are due. And I'm going to post the makeups for the exam online. Have a good Thanksgiving.